That is concerning. No, it is not. That's what everyone said, but that is not what it is. Yes. Yeah. Derivative of ln is 1 over x. All right, good. The correct answer is catching up. I like it. All right, I'm going to wrap this in 30 seconds. All right, and people run out of time. Too late. All right, here we go. We've got this like upside down staircase, or I guess it's a staircase in the white if you want to take it that way. Yeah, luckily A, so A is the correct answer. I was a little bit worried there. B kind of jumped out to an early lead, but A is the correct answer. And the important thing to remember here, right? Actually, here, let me write this down. So the important thing to remember is we have a couple of rules, right? So we know, for example, that the derivative remember we had this conversation, if you have a constant in the exponent, then you can use the power rule, right? But if the variable is in the exponent, then you have to, do something a little bit different, right? That's different. That's not the power rule. But now the question is like, what do you do if you have an x both in the base and the exponent, right? How do you deal with this? So how do you deal with something like this? Right? We talked about this. This is the logarithmic differentiation portion. So the function we have, so our function is f of x, but is x squared plus x to the power of x. So x squared plus x to the power of x, like that. Okay. And the trick that when we do this, it's actually possible to do this one using implicit differentiation if you want to, but using logarithmic differentiation, what we're going to do is we're going to take ln of both sides. Take ln of both sides. Okay, and if we do that, what do we get? We get ln f of x is ln x squared plus x to the power of x. And now we're going to use that special property about logarithms that let us take the exponent, down, right? So it's not an exponent anymore. And this is the whole power of using logarithms here, because this isn't an exponent anymore, right? Okay, now what we're going to do is we're just going to differentiate both sides. And now here's where we use that thing that we talked about on Tuesday, right? When we talked about what is the derivative of ln f of x? Well, we said it's f prime over f, right? That was one of the things that we found. So now differentiate. Okay, on the left-hand side, we get f prime of x divided by f of x. And the right-hand side, okay, we have to use the product rule. So derivative of the first is x times the second plus x times the derivative of ln x squared plus x. So we get 1 over x squared plus x times the derivative of that, which is 2x plus 1. And so we get ln x squared plus x plus 2. How did I write it in the thing? Derivative of the first times the second plus derivative of the second times the first. 2x plus 1 times x divided by, oh, we can cancel some x's though, right? So we can cancel this x and that. So that gives me x plus 1 in the denominator, right? Josefa, yeah, I probably can, but just give me a second. And now when we want to solve for this, right? So this is one of the answers. This is actually C. So for those of you who did C, I think you did like the correct thing here. But what you forgot to do is say, I'm actually trying to solve for f prime, not f prime over f. So when we solve then for f prime, we multiply everything by f of x, right? Times this stuff. I don't want to write it all down again. I will for the final answer, but that gives us then x squared plus x to the x on the 2x plus 1, that's the derivative of x squared plus x. Like so. Okay. And so Josefa, just really quickly, right? I don't want to go into this one in too much detail, but we did do it on Tuesday, so you can check that video again if you want more. So when we differentiate this thing, right? So derivative of the outside, so ln, the derivative of ln is 1 over x. So I get 1 over f of x, right? Because you evaluate it at the inside function, and then you differentiate the inside function. So you get f prime of x like that, right? And that's f prime of x over f of x, right? Like that. Okay, cool. What if we don't put ln on both sides? Can we just get the answer by applying the chain rule? No. Well, you can if you know what to do, but like what chains, like what two functions do you want to use? Right. So our goal here is if we want to go straight. Yeah. So the thing is, this can be done if you use implicit differentiation, but the problem is that it's hard to write this as a composition of two functions, right? Is there anything we'd be able to do for this? Not really. This one's pretty tough. I would say like you'd be in a really hard situation to solve this one using just the chain rule. In the special case where you have something like, let's say the exponent and the base were the same, right? So if we had this function, let's call it a different name, g of x, and it looks something like x squared plus x to the power of x squared plus x. This time you could do it because you could say let one function be x to the power of x, and the other function, maybe let's call it k, be x squared plus 1. So now this function is h compose k of x. But the problem in doing this is you still need to know what the derivative of this is, right? And this is one of those ones that like you might just know. This is x to the x ln x plus 1. But basically the way that you actually determine that this is the derivative is to do exactly what we just did. So basically, it seems like no matter what you do, you can't really avoid the logarithmic differentiation, like taking ln of both sides. They're just, at the end of the day, there isn't much you can do to avoid that, right? Like I said, there are actually a couple of other ways that you can do this. If you have higher order derivatives, or if you have multivariate calculus, there is a way of doing this without having to take ln of both sides. But obviously, we don't have that available to us, right? So for this sort of thing, yeah, if you see it, your variable both in the base and the exponent, big hint is you take the ln of both sides. Okay? Any questions, anyone? There's this wonderful problem that we used to give in MAT133, right? We trained those are the advanced calc students. So we trained them to do this problem, and we managed to give them a test question, which we were super confident they would all get 100% on. And then the average on that question was 11%, right? Like they did so poorly on that question. And it's wonderful. So I'm going to give it to you as a little exercise, and I want you to tell me if you can get it. And we're like, I really hope you all kick the butts of that class of 137 students. It would make me so happy. So let's suppose f and g are both differentiable. Are differentiable. What is this derivative? Okay, so I'm going to take f of x to the power of f of x. I'm going to add it to g of x to the power of g of x. And I want you to differentiate that function. Okay. So you can see, like, and this is the sort of thing you can probably imagine you actually could get on a test. Like, I don't think that this is in particular a 137 question. I think you all should be able to do this by the time the next test comes up. And so the question is, how many of you get the right answer? And I hope overwhelmingly that I can then go to, the 137 students and be like, yeah, the 133 students got this. So, it can be done. Like, what's their excuse? So please, I hope that you all give me that ability to just laugh at them. But if you get it wrong, then on the other hand, you can be like, listen, the advanced calc students couldn't get this one either. What chance did I have? But I have confidence in you. You all have the tools to do this. I'm certain that you could do it. Okay. All right. Let's do another one. I think this is going to freak some people out, but that's life. Oops, shoot. There we go. Yeah, right? This sort of thing is also totally fair game. You could do this. Okay, listen, everyone. Problem solving 101, right? Problem solving 101. Right now, this function has, like, if you were to expand this out, it's like x to the power of 2022, right? Like we're multiplying a bunch of these things. But let's say I gave you this question on an actual, like an in-person final or an in-person exam. Why not do it for like just x plus 1, x plus 2, and x plus 3 and see what answer you get, and then see if that answer shows up. Like, obviously the number 2022 doesn't actually matter here, right? So as sort of like a test taking strategy, if you were to do this on a test, do it for x plus 1, x plus 2, x plus 3, and then stop there, differentiate, see what answer you get, and see if that answer shows up.
It was a very uniform distribution for like exactly 2 seconds there.
Yeah. Yes, it was. It was nice. There's still chance. There's still hope. A lot of people forgot the chain rule exists. But the reality is you don't even need the chain rule to do this problem. This problem is actually really straightforward, and it's going to make you all so upset when you see the answer.
That's true.
So upset. You're going to look at this and you're going to be like, oh yeah, I totally could have done that. Oh man, correct answer, just big surge. I mean, you will eventually, depending on how you do this question, that you might have to do the product rule, right? You might have to do 2022 applications of the product rule, but there's a very clear pattern if you do it that way, right? And this is one of those things that, like, if you're not certain and you don't see the pattern, try doing it again for like just the product from x plus 1 to x plus 3, and you'll see that there's a lot of cancellation when you do that. And then you'd be like, oh, maybe there was an easier way. And the answer is there is. I used to play this game with our students when we would do this more in person. And what it was is I teach them how to do logarithmic differentiation, and then I'd say, okay, stump me, see if you can stump me. So I'd say, give me the nastiest functions you can, right? We're going to make this big, ugly thing. We're going to like multiply these functions together. We're going to raise functions to other functions. Like, give me the grossest thing you possibly can think of. And they would spit out stuff. I would take answers from the entire class. And it was funny too, because you got like a bunch of students who didn't normally contribute, but the moment there was a challenge on the table to try and defeat me, everyone got involved and was really excited. And so then I'll write down, big and ugly functions. And then I would use logarithmic differentiation and just like, solve it in a matter of a couple of seconds. And it all made them like so angry. But I think it made the point that like logarithmic differentiation is actually a really powerful thing. So hopefully you all get that too. I'm going to wrap this up in 20 seconds here. That's pretty uniform, Aziz. Like it is. It's pretty close. 10 seconds.
You always say like this type of distribution means people are just guessing.
Yeah. Oh, we got our staircase back. All right, let's take a look at this. All right, I don't know, like there's a big change in the distribution right towards the end. A bunch of people wrote down A, don't know if it was a guess. A is the correct answer. And again, I think a lot of people are going to be really, really angry when you see this problem. So, okay, does everyone remember the following? So let's say this is question 7. Maybe let me just label that. So question 7. So let's say recall ln of AB is ln of A plus ln of B, right? Everyone agrees? The logarithm satisfies that, so it turns products into addition. Yeah. And so ln of x plus 1 ... x plus 2022 is ln of x plus 1 plus ln of x plus 2 plus ... plus ln of x plus 2022. And now when you differentiate, Oh, Agam, as a previous thing? Yeah, let me check that in a second. So now differentiating. And we get, oops. For some reason, it's not ignoring my palm anymore. So if we differentiate, that's the same thing as differentiating the sum, but you can, when you take the derivative of the sums, you just take the derivative of each of their pieces, right? So you get 1 over x plus 1 plus 1 over x plus 2 plus dot 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 plus 1 over x plus 2022. And that's the answer, but if you want to write it in fancy sigma notation, it's that. Okay. And now you didn't have to use that if you didn't want to. Let me show you what I mean. Like when I say, what if you had just done the product of the first three things, like x plus 1, x plus 2, and so on. And again, problem solving, a good problem solving technique is if there are really big numbers, try to do it in a smaller things. Well, Namir, why don't you write it down and I'll tell you whether or not you got it. Okay, so if we were to do this, what would we get? We would get 1 over x plus 1, x plus 2, x plus 3. And then we have to product rule through all of them. Okay, then write it, take a picture, and send it. Okay, so now I have to product rule over it. And when I product rule, I get this. Because I don't want to, I just don't want to spoil it for any of your other classmates if they're working on it as well. Okay, so if you do it that way, you get this. And what you notice is that when you differentiate the first function, it disappears. When you differentiate the second one, it disappears. When you differentiate the third one, it disappears. And if you expand this out, like there's going to be tons of cancellation and you're going to get the exact same thing. Like that, right? So you get the same thing either way. So that's the idea there. Let me check what you did. On truth, close, right? Let me just double check here. So you get F, so you get oh yeah, never mind. That does cancel. 1 plus Agam. Yes, your answer is correct. So good job. You beat 89% of the 137 students on this question. So good job. Very good job. Okay, any other questions about this one? Is that okay? Everyone's good? Right? This is a great question. I love this. Did anyone look at this and be like, oh yeah, that wasn't too bad? Right? I think it's one of those questions, again, where like, if you were to see this on a test, a lot of you would have started panicking. I think like most of you started panicking here. It wasn't even a test. But, take your time, think about, are there any special properties of this function that I could use to make my life a little bit easier? Log, right? This is the entire purpose of using logarithms to help us differentiate, is it turns, remember, what's the rule here? It turns exponentiation into multiplication, and it turns multiplication into addition. It seems to make it I think addition is the easiest, and then multiplication, and then exponentiation, right? And logarithms always take a step down the difficulty ladder. So they take exponents and turn them into multiplication, and it turns multiplication and turns it into addition. So logarithms take a step down the complexity ladder. That's why we want to use them, right? So if you see log of a big product, that's a good sign that you should probably use logarithmic differentiation. Okay. No, I'm going to skip that. I'm going to go to implicit differentiation. I want to make sure we get a little bit of that in. So I'm going to skip these. All right, let's try that one.
The fun stuff.
Yeah. I think you'll really like the implicit differentiation. It's very computational, right? Yes, integrals are next. Well, not next week. They're after
Okay,
the reading.
don't we have to like? Are we doing any like optimization?
Yeah. So that's
Okay.
next week. Yeah, and then after that we'll do integrals. So Curdy, they're the next section, but not the next week, in that sense. Depends what you mean. I mean, no. I think you all have a test after the reading week. So on the Friday after the reading week, if I recall. And so this is, yeah, the benefit of this is you don't have anything due after the reading week. So you can just spend your time to catch. And this was actually by design. I tried to plan it this way because I hate giving students stuff that's due over the reading week. I think the reading week should be an opportunity for you to like catch up and stuff. So yeah, test 5 is the week after the reading week. So you will hand in assignment 10 on the Friday before reading week. You have no responsibilities in 133 for that reading week other than to catch up if you're behind. When we come back that week, there'll be test 5 at the end of that week. So you can basically spend 2 weeks studying if you really wanted to.
Mm-hmm.
And it'll be just differentiation. That'll be the only thing that we do for that test. Mm-hmm. Yeah, it's true. Because, I've had lots of students say like, oh yeah, it's the reading week, but my prof knew it was reading week and so assigned us extra work. And I'm like, well, that's stupid. That defeats the entire purpose of reading week, right? Like, I mean, yeah, okay. And I mean, in some extent, that's okay if they were kind of like, had to do them in the class anyway. You know what I mean? Like reading week is supposed to be historically, right? It's the opportunity where you caught up, and it's typically where you caught up on your readings. That's why it's called the reading week, right? So it's where you catch up on your readings. If you assign extra work on a reading week, that's stupid, right? Because then students can't catch up. So the entire point, like you're not necessarily supposed to go to a beach down south and hang out in the sun. You can do that if you want, but it's supposed to be for you to catch up. And sometimes catching up means doing some assignments, right, that need to be done. And if you finish this question, I want you to do Dxdy. Okay. So if you finish this, like you've done dy dx, if you finish this question, I want you to flip it around and do the other one, do Dxdy. And you should practice doing that one a little bit just because 100% we could ask you that. And it feels weird to differentiate with y as being the independent variable. So it's not a bad idea to give it a shot. All right, 30 seconds. That's crazy to me. On my Surface and on my computer, the time that the poll has been up have two different numbers.
Well, what time do you have? Does I have a number as well?
Okay, so my computer says 5:20 right now.
Oh, mine says 5:09 when you said 5:20.
5:09?
Yep.
Yeah, that's what my Surface says. So it's weird that they keep time differently.
That is very weird.
Very weird. Okay, I'm calling it. Oh man, only half of you answered. Some of you weren't. Okay, so that's good. 41% of the class said B, so we have a plurality in the right answer. Namir, you're right. Because, yes, exactly. Yeah, good job. And so, yeah, again, and if any of you who got the right answer are confident, you don't want to watch me do it, again, start working on Dxdy. So let's do this one. Which question is this? This is question 10. Okay, so we have x squared y cubed is equal to 1, right? We're going to solve this, differentiate this implicitly. Now, as I make clear in the video, I think the main thing that students struggle with when they're doing implicit differentiation is you have to remember you're pretending that y depends on x here, right? You're pretending that y depends on x. So when we differentiate, right? Let me write out the product rule kind of in more detail. So again, we're going to differentiate the first times the second plus the second times the derivative of the first. And the derivative of 1 is just 0, right? Okay, now the first thing here, no problem, 2xy cubed, right? But when we get to this thing, remember, we're pretending y is a function of x. So we actually have to chain rule this. So we get 3y squared dy dx. Okay. And now when we solve for dy dx, right? So I'm going to move this thing over here. So I'm going to get 3x squared. Sorry, this should be y squared dy dx is negative 2xy cubed. Then I'm going to divide by 3x squared y squared. So I get negative 2xy cubed divided by 3x squared y squared. And I just try and do as much cancellation as I can. And I get negative 2y over 3x. Okay. And that was option B. Voila. So again, kind of a good exercise. Maybe let me write it down explicitly here. Exercise. What is dx dy, right? And again, notice here, the x is in the top and the y is in the bottom. How do you get 3y squared dy dx? Okay, sure. So here, right, this is kind of the critical thing about implicit differentiation. So for this thing, we're going d dx, and here, let me abuse notation a little bit. Yeah, it's the derivative of y cubed. Here, let me write it like y of x cubed, right? Like we're pretending y depends on x, right? That it's a function of x. And so if this were a function of x, what would you get? Well, we'd have to chain rule it, right? We'd get 3y of x squared y prime of x, right? And that's the same thing as 3y squared dy dx. So when we do the implicit differentiation step, we're pretending that y is a function, not just a variable. It's actually a function of the x variable, and therefore needs to be chain rule differentiated, right? Does that make sense, Brandon? Cool. And so basically, I mean, kind of like as a bad rule of thumb, I don't really want to give you this strategy, but the general rule is that you can basically differentiate the function with respect to y and then just tack on a dy dx at the end. That's always how it ends up working out. But I mean, that's kind of a bad way of doing it. Okay. Again, as an exercise, try and compute dx dy. Okay, it is actually one of the answers that was in the multiple choice. So it is one of the answers. And then more importantly, and I do talk about this in the video, but you might have forgotten it. So very importantly, what is the relationship between dy dx and dx dy, right? And try and nail that one down. Okay, I really want to get through one more because I think this one is important because a lot of students make a mistake that this question has.
Today, like today and yesterday, I guess on Tuesday tutorials, I was asking the students what f of x all squared is, like what the derivative, sorry, of f of x all squared is.
Mhm.
And 80% of them got it wrong.
Well, 80% of them better start getting it right.
I told them, I'm like, it's better to get it wrong in the tutorial than to get it wrong on a test or assignment.
Yeah, exactly.
It's
right.
it's not a bad thing, but it was more than I thought. I had like my guess was like 20% of the class is gonna get it wrong, but 80% got it wrong. So
yeah.
very
Again,
surprised.
maybe hopefully that'll just serve as like a wake up that, you have to like really go at it.
Because most of them just said 2f of x, right? So like they didn't actually do the chain rule component, just multiply by f prime of x. So it's the mistake I expected, but just the volume is what kind of was like questionable. I mean, not everyone answers in the chat, so maybe like the people that didn't answer knew the answer implicitly, but didn't actually verbalize it. But
yeah, I'm hoping that maybe this is just like it's a heavy week or something, because I think a bunch of people were saying there were a bunch of term tests. And so, hopefully it's just a heavy week and maybe people are a little behind, but yeah, otherwise. Kurt, are you asking Aziz?
yeah, I think so. I'll type up in the chat. It's not really that complicated.
Yeah, the common mistakes that we see in implicit differentiation when students are doing it are that they do forget to use the chain rule, or they remember to use the chain rule sometimes and then forget to use it the other times, right? Which results in some f primes not showing up, or dy dx is not showing up. So just be careful about that, everyone, right? Like if you're differentiating y with respect to x, a dy dx should show up somewhere. Yeah, you could. Yeah, for Aziz's question, you absolutely could use the product rule for that. If you didn't want to chain rule it, yeah, totally you could.
That's a great point.
Yeah. Yeah, right, is f of x squared, or like f of x times f of x, and then different derivative of the first, and you get the same answer, right, either way. Again, that's one of the nice things about calculus is you have all these different rules, and you can use whatever rules you want in whatever order you want, as long as what you do is legal, and you'll always guaranteed you get the right answer. Even if you did things in sort of like a weird way, you'll always get the right answer. The rules are always consistent. This is a super cool thing. All right. Start getting your answers in, people. No, this derivative is a bit tricky to compute, though. That's fair. If you have to take a second and compute that derivative, it's not an easy one to compute. It just hurts the brain, I think, right? When you do this one. Yeah. Because it's backwards, it's got a chain rule in it, it's got a product rule. In fact, everyone's going to have to double check mine to make sure I do it correct. Hopefully I will. Okay. Yeah. Yeah. Yeah, it's gonna be a thing. But like, how about this? Let's say if it was e to the power of x times f of x, or e to the power of y times f of y, could you do it then? right? Like in this case, it's kind of weird because we're differentiating with respect to y. Okay. But yeah, if I asked you to do something like this, right? Could you do that? That one's probably feels not as crazy, right? But that is the same thing as what we're doing. We're pretending that x is a function of y. So I've just called that f of y here. And if you can do that derivative, then you can do the derivative of e to the xy. Okay, I'm going to call it in 25 seconds.
I'm trying to do it in my head, but I keep on losing track
Yeah.
of times.
Yeah, it's a little bit nasty to do. It's kind of, I think, surprising given that it's such a small thing and yet is surprisingly like tricky to work through. All right, let's take a look at this. We're pretty split, right? I think that's about as close to being a uniform distribution as we typically might get. The correct answer here is A. Okay, so there's a couple of things that we actually have to do for this problem. And just for the records, this is 100% a kind of typical question that you could get, right? In fact, if you kind of look at the next assignment, you'll see that it's very similar as well. So why is, oh, because I'm still in annotate mode. No wonder. How do I turn off annotation? Okay. So this is question 11. Question 11. Okay, and again, we've got x e to the x y equals 2, and we want dx dy when y equals 0. Now, one of the things that you may have noticed is that all of the answers were numbers. They weren't like the previous question where they were like, in terms of x's and y's and stuff, we actually wanted a number out. And the big suggestion that